All right, it's time to get started. Before we do, we have a couple of important announcements. I posted an assignment on Canvas on Friday that is due Wednesday evening. Everybody received that?
Next Wednesday, right?
It's the meeting 17th about that. Oh, I think I meant for it to be this Wednesday. Week from Wednesday would be probably just a little long. So hopefully people can get started with that today if you have not already and come prepared with questions. I anticipate there will be quite a few questions regarding the assignment. It ended up being a little bit longer than I had originally designed it to be or intended, as I realized, hey, I can add this to it, or I can modify it to have this outcome as well. So it came together. It was a little bit bigger than I had intended, but I also think it will be really useful to all of you to reinforce some of the 211 concepts and start getting you some additional practice with linked list design. And it will be augmented with what we cover this week. The second important announcement is that APE registration is open, but only for the next week. The deadline for it is the 15th. So you have 1 week to register for the APE. If you have not yet passed the APE, this is something that you absolutely want to be doing this quarter. There is no reason not to. We'll have covered everything that you need for the APE by the time the APE rolls around. There are a couple other topics beyond this that will be necessary to go over. Mainly, we will be talking about recursion and we will be talking about sorting. So both of those topics will be over the next couple of weeks, but it didn't take me very long to change up the schedule or the anticipated schedule on the syllabus. This was originally the 4th thing we were going to cover, and I've moved it up to the 2nd thing we are going to cover and pushed back each of the original 2nd and 3rd things to be the 3rd and 4th things. And that is because going over computational complexity will help us to be able to add some extra things to our discussions of the other elements that we would otherwise have to come back to after we talked about complexity. So that's where we are. Are there any questions or concerns at the moment about the assignment? About anything that we've covered in class?
So the time's gonna do this Wednesday for sure.
That is what I meant for it to be. We will see how people are doing. If the entire class struggles on something and it doesn't look like the class as a whole is going to be successful by the due date, then I remain open to pushing it back. But I'll let the class decide kind of on that. So don't anticipate it being pushed back, but if you are getting stuck, don't stress out too much because you're probably not the only one. And then I'll work with where you are. All right, let's get started. This is one of my favorite topics in this course. In fact, it might even be my favorite topic, and I anticipate it will not be very many of yours. But I will try to make it as engaging and interesting as possible because it is very, very important to the essence of computer science, to what you will be thinking about for the rest of your career if you go into computer science. So for most topics that I cover via a reasonable amount via slides, I try to motivate what we are doing. It's very important. So let's assume that we have 2 competing algorithms that are going to solve the same problem. So we could either apply algorithm 1 to solve the problem or algorithm 2 to solve the problem. We know that they both solve the problem, but the question is which one of them is better. So here is what we want. I need to retrieve a value from a list. So which type of list is going to be faster at retrieving elements? Is it going to be an array list or is it going to be a linked list? So think about that for a little bit and see if you can come up with an answer as to which list type is going to be better at this. Anybody have a guess?
Array list.
Array list? Anybody else with a guess? Yeah,
Linked list.
linked list. All right, we have someone going against the one trend we have. I love it. So if we had to do a best guess at this point, who would think that the answer would be an array list? It's about half the class. How about a linked list? Who thinks a linked list is going to be faster? Fewer people, but not nobody. Excellent. So for those who made a decision about this, what information were you considering when you made this decision? So yeah, we definitely need an index to get, we'd be retrieving, it doesn't really matter if it's looking for a particular value in the list or retrieving it needs to be retrieving in a particular index. But let's say we want to get the 20th element of the list. Yeah,
Well, what I thought was like for a loop list, you have to loop through each single one to find it, so.
yeah, we wrote a loop for the linked lists get that started at the head and was saying dot next, dot next, dot next, dot next, dot next 20 times. How does an array list handle its get?
It's sorted in array.
Right. Yeah, so the position of the index in memory is basic arithmetic. You take the index times the size of an element and it tells you, you can just kind of teleport into the array list and grab the associated index. There's no looping that is required. So these kinds of questions permeate the field. You will always be asking yourself, given two competing algorithms or more than two competing algorithms, which one is going to be better in this particular situation? So having the tools to be able to answer that kind of question is really important. So one way that you could actually go about this process to try to verify, is one going to be faster than the other? You could imagine writing a program that used a timer of some kind, kind of like a stopwatch, to time the procedure and figure out, okay, how long did it actually take to do this? So here would be an example of such a program. So we'll call it time test. You will give a static final integer that is the length of the list. We are going to go through the list and add something to each element of the list. So elements indices 0 through 99 are going to have something in it. And then we are going to grab the current system time. And if anyone knows how the current system time is stored, it's in the number of milliseconds that have elapsed since January 1st, 1970. So it ends up being quite a lot. So to do this, we can't actually store it as an int, we need to store it as a long. We talked a little bit about this last week, about how we overflow the maximum size of an integer. We actually need to use a different primitive type. A long, that instead of using 32 bits for storage, uses 64 bits. And it doesn't just allow you to represent numbers that are twice as large, it's twice as many bits. So instead of 2 to the 32nd, we can store up to 2 to the 64th, which ends up being an extremely large difference. And longs can handle most interesting computation that we care about. We have to use some less exciting tools if we overflow a long. There is a long, but beyond that, we need some kind of new way to store numbers. So we grab the time before we grab the element, and then we grab the element, and then we store the time after we grab the element, and then we print out the time difference, difference in milliseconds between when we started this and ended this since January 1st, 1970. So we are going to make an array list, test it with an array list, make a linked list, test it with a linked list. Any guesses as to the what kind of output we would expect for this? No guesses? We're doing a single get of the fifth element of the array list and the linked list? The answer is not enough to register. Regardless of what we choose, computers are so fast that this individual test doesn't really tell us anything. So that wasn't particularly helpful. We learned that computers are fast, but we kind of already knew this. So what could we do? How could we modify this idea to actually be able to identify which one of these is faster at get?
Could increase the size of the list.
Definitely, we could make a longer list than trying to get the fifth element. That's a great idea. Any other ideas? What if we really wanted to know just about getting the fifth element? We could get the fifth element a bunch of times. If we were to throw this inside of a loop and try it a bunch of times, maybe it would register in a number of milliseconds that we could actually use to compare. So either one of these ideas would be good, but they measure slightly different things. So we're going to start by wrapping the call in a loop a bunch of times. Do note that when we start to measure this in milliseconds, this is going to depend on a few different variables that are worth considering. These answers are not the exact answers that you would get if you ran this on your machine, if I ran this on my machine. This is just illustrative for a particular machine running this once. So it will vary per run because how long it takes to allocate that memory actually slightly varies. It'll vary per machine in that if you have a faster machine, this entire process will be faster. But note that any differences that we see here will continue to be differences no matter which machine we run it on. So the exact values will vary, but the reasoning behind it will not. So what behavior do we expect if we get element 50 rather than 5? We expect exactly the same difference. Close. Other ideas, other guesses? Yeah, it's basically still 0 because it's not. But if you were able to compare the actual difference, the difference between the array list and the linked list, would it be about the same grabbing element 5 and element 50? Would the difference be larger? Would the difference be smaller? What would we expect there? Larger? That's going to end up being correct because if we're grabbing element 50, that's more iterations through the loop. In fact, it's 10 times more iterations through the linked lists loop. And the array list is still able to use basic arithmetic to just go grab the associated index. So the array list may not vary much, if at all. And the linked list will take significantly longer with this. So here's a program that would actually go test it. We're going to run this test a billion, is that million times? I'm going to run this test a million times, and we are going to get the fifth element a million times. If your computer could think, it would hate you. This is the equivalent of doing something like, all right, solve a math problem and show your work, and now do it 999,999 more times. The exact same problem, no more learning outcome. It's not even a similar problem. It's exactly the same problem. You have to show your work and show your work and show your work. It's a good thing we have computers. So if we did this in a loop, we end up with a bit of a difference. The array list takes 21 milliseconds to get the fifth element 1 million times. The linked list takes 39 milliseconds. This is intriguing. So now we're starting to see an actual difference. We're actually starting to see that the array list is doing this faster than the linked list. If we get element 50 rather than 5, we need to think about the actual underlying code. An array list gets the value at an index by straight up multiplication. We know the memory address of where this array list starts in memory. And we know that they are all contiguous. All of the elements in the array list are right next to each other in memory. When we go make an array list, we have to specify the associated size of the array list. If it's just an array, you have to specify the associated size. An array list is capable of resizing, but that can end up being very expensive if there's not enough contiguous space in memory right there for that resize. It needs to go find a new place to store the new array list, make it bigger, some kind of contiguous space that's bigger than the original, and then copy over all of the elements from the original array list into the new array list. And that ends up being fairly expensive. So that's if you're adding to an array list, but if we're just getting the value, there's no possible resize. The linked list actually has to go iterate through its loop to find the value at an index. So we find that if we're looking at getting the 50th element instead of the 5th element, here's what we find. Did the array lists take longer? No. This actually makes sense if we look at the underlying code. It's not doing anything in a loop. It's not repeating the same logic over and over. It's just an addition and a multiplication. That's it. Regardless of where in the array list we are trying to go, it's always an addition and a multiplication. The linked list, on the other hand, needs to do that iterative process. So now, instead of looping through 5 times to find the 5th element 1 million times, it has to loop through 50 times to find the associated element 1 million times. So we would expect it to take about 10 times longer. In practice, it's not quite 10 times longer. So I answered my own questions here. It didn't take it more time because it's still the same amount of work. It doesn't matter how big the addition and multiplication is, because it's always a 32-bit manipulation. The integer that's stored in that work is 32 bits, no matter what value it is. So it's the same amount of work to do a multiply, whether it is a small value or a larger value. So it takes the linked list longer because it actually has to go through that loop. All right, important question time. We have now shown that an array list gets faster than a linked list. Is an array list just better than a linked list?
No,
No? Why not? What makes you say that?
because I feel like linked lists they thrive in other areas that array lists don't.
Sure. There are pros and cons to each one of these. We just isolated one of the cases where an array list outperforms a linked list. Where do we think that a linked list might outperform an array list? Removing an element, potentially adding an element. We will look at this method by method later on. This might end up being tomorrow, but I actually want to have an epic battle between the array list and the linked list. And we're going to pit them against each other in some kind of weird algorithm fighting ring. And we will see which one comes out on top. So the next question I might ask is if we wanted to get an index significantly higher than 50, because if you're implementing these in some kind of work-related setting, you're probably not making an array list or a linked list of size 50. You're probably making one that is significantly larger. So if we're trying to query and get the index that is higher than that, what would we expect? Yeah. The gap between how long it takes for an array list and how long it takes for a linked list would increase. That is what we would expect. Absolutely. So the array list get method does not rely at all on the index that it's passed. Same amount of work. However, the linked list get does depend on the index passed, and it will take an amount of time proportional to that value. it's worth actually thinking about when you're trying to decide between an array list and a linked list. So the conclusion would be, we need a list. We know we're going to be retrieving without removing elements frequently. We would then start to bias ourselves toward using an array list instead of a linked list. Because we want the query of the get to take 22 milliseconds instead of maybe an average of hundreds of milliseconds. Thousands of milliseconds. Questions on any of the work that we've done between the array list and the linked list?
So we just use the term linked list, but you know, there are a few different types of linked lists.
Yes, for the most part, it does not matter. Most linked lists will have the same associated logic. Because in order to do something like we have a doubly linked list and we want to get the index, there's no way to teleport to the associated node. We still have to iterate, even though we could iterate backwards from the tail if we had some inkling that it was toward the back of the list instead of the front of the list, or we knew it was the tail, we could teleport directly to the tail. But at least on average, we'd be getting something closer to the middle of the list, and so we would have to work our way inwards still inside of a loop, regardless of that. Unless we wanted to store some way to teleport across all of the lists, which means that each node would have a number of references equal to the rest of the nodes, but we still have to know where to go. Which would be hugely wasteful in storage. So where we're going with all of this is we want to start having some generic way of communicating running times that aren't necessarily just in milliseconds, because we know that the milliseconds vary between machine to machine, between the index that we're actually calling. So we need some way to communicate this concept in a way that is going to be understandable by everybody and is machine agnostic, meaning that it doesn't depend on the machine that it's being run on. So think we have two methods we want to compare. You can use the example that we just did in your head if you'd like, the array list get and linked list get. If we decided to start doing what we had done before for a bunch of different values of the input size. So get the first element, get the second element, get the third element, get the fourth element, get the fifth element, etc. We could start building a table where we would have the value of the index of the get, and we would have the associated number of milliseconds that it takes. And that would be our two axes for some kind of mathematical function. We could plot those. X-axis is the size of the input, and the y-axis is the associated running time in milliseconds. What do we think this kind of work shows us? Yeah, we could figure out exactly how. We can find some mathematical function that it's not just a list of milliseconds. We can actually give a mathematical function in terms of the size of the input. That is super useful. So we can compare known mathematical functions against each other to determine the behavior and whether or not one algorithm is better than another without having to look at long tables of milliseconds. So let's take an example for the moment. We're going to say that when we plot these on this associated graph, we find that the first method gives us the following expression, 10n squared minus 5. And the second one gives us 100n plus 200. Without doing any work on a computer, take out a piece of paper and draw what you think these expressions look like on the same graph. X-axis between 0 and 20. Y-axis, whatever you think you need it to be. We don't care about negatives, we only care about 0 to 20 on the x-axis. Feel free to talk this out with your neighbor or neighbors if you'd like to. I think we might be mostly done. Who'd like some additional time? All right. Now, I would like to see a set of thumbs. How confident are you in your image? Confident, kind of have the right idea, but not 100% sure. Almost certainly wrong. Kind of, sort of. I see stuff that's all over the map, which is great. So the actual image looks like this. Note that the y-axis is pretty significantly larger than the x-axis. So we go from 0 to 20, and we see an inflection point in this graph. So let's first, just in general, query what do we notice about the graph? So I'll zoom back in so people can see it. What do we notice about the graph?
A is exponential, B is linear.
So we have a quadratic function, you have a linear function. So one increases at an increasing rate and one increases at a constant rate. What else?
One of them will have digits at the beginning and one is second.
Yeah, so we have this weird aspect of this where if n were less than 12, we might prefer the quadratic function, the linear function. But if n is greater than 12, we might prefer the linear to the quadratic. So we notice that the quadratic method is faster if n is less than 12. The linear method is faster if n is greater than 12. At n equals 12, we don't care. It's the inflection point. They have exactly the same performance, expected performance. Great. This is a very useful tool for being able to think about and analyze running times of algorithms. But let's start to think about how we could get out of this. This is a little bit too exciting. So scales are also incredibly important if you're looking at graphs. We know this from elementary graph analysis. But now, think about what this graph would look like if we restricted the x-axis from 1 to 6. Go ahead and see if you can draw out what you think it looks like from n equals 1 to 6. Kind of a zoomed in image on this portion of the graph. It ended up looking something like this. If we were to just look at this graph and not the prior graph, what kind of incorrect conclusion do you think you could draw from? Yeah, it looks like from this perspective that this algorithm is always outperforming this algorithm. Is that true? No. Is there evidence in this graph that suggests we should consider a different scale? Yeah. Valid. So we see that this is starting to increase at a more increasing rate as we get toward the edge of this graph, which means that the distance between this function and this function is going to start decreasing. So if you start thinking about it in terms of derivatives and calculus, then you might start to think about, maybe we should look at this at a slightly different scale. So we see as we analyze mathematical functions that certain parts of those functions matter significantly less than others. So dealing with constants like the 10n squared minus 5, the minus 5 matters less and less and less as n scales. Does that make sense? At n equals 1, 1 squared is 1 times 10 is 10. So the minus 5 is useful. It's creating half the distance between 0 and where it could end up without it. So it has a significant effect. But now we set n to 10,000. Now set it to 1,000 to make our life just a little bit easier. 1,000 times 1,000 is 1,000,000. 10 times 1,000,000 is 10 million. Now the minus 5 is a minuscule portion of this function. So some elements of the function scale significantly more than others. The minus 5 does not scale at all. As computer scientists, we don't really care what happens when n is really, really small. Why do we think that is? That n between 1 and 6 range, where the quadratic function looks better than the linear function, why don't we really care about that region?
Often we're writing programs that are just 2 lines of code.
Yeah, yeah, for something that's that small, but also computers are so fast that even if you have something that's horribly inefficient, you give it something of really small size, and it will be able to finish that in a matter of milliseconds. It will not be noticeable to the human eye, the human brain. So efficiency doesn't matter very much at the small end of the scale, but it will start to matter a ton at the larger end of the scale. As we start to blow this up, the quadratic function is going to look worse and worse and worse and worse compared to the linear function. So difference between the functions for small n, it'll be so small it doesn't matter in practice, but We care about how our design scales as we increase the size of n toward what we're actually going to see in practice. When we can actually noticeably tell the difference between two algorithms. So to be able to do this, the tool that we're going to want to use is we want to classify these functions into orders that describe the long-term growth of the function. So how does the running time increase as n gets very large? And it turns out that a lot of the difference that we see between functions in the same order just does not matter if the scale reaches large enough. So the terminology that we're going to use and the symbols that we're going to use for this, for every function f, theta of f, or we can define this to be the order of f, defines the placement in this order table. Each order has an infinitely large number of functions that belong to that order. So there's not like there's just a few of them associated with each order. There's one order, and there are many, 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 many infinite functions that belong to that order. We will see exactly what this looks like, and I'll motivate it here more in just a little bit. Any questions about the terminology or what it means? Yeah,
What's that symbol?
it is a capital theta, capital Greek theta. So if you hear anyone say or discuss theta of n, the order of n, big theta of n, any of those describe this exact concept. The order of some function. So let's actually take a deeper dive into what these orders are and what they represent. Here's a table of common orders in computer science, and I already hate the table because it omits two nicknames that we actually have names for. So these are actually listed. At the top is very inefficient, and at the bottom is very efficient. So inefficient to efficient. That's kind of opposite of the direction of thumb you would expect. Efficient is thumbs down. So constant time means that regardless of the size of the input, the algorithm performs the same. We just saw this with the array list get. It doesn't matter how big the array list is, to call get on an arbitrarily large element will take the same amount of time as it takes to call get on something toward the beginning of the list. So the array list get belongs to this order. It doesn't get better than this. We can now start questioning what happens as this starts to scale, as things start to take a little bit longer and starts to matter with proportion to the input of the size of the input for the algorithm. So we can get logarithmic scaling. We see this a lot when it comes to trees, tree structures. Linear was the order of the linked lists get, because we had to go through a loop some number of times that was proportional to the index that we were querying. If the index was 5, we had to go through a loop 5 times. If the index was 50, we had to go through a loop 50 times. If we were to build out that table, it would be directly proportional. Whatever the value of the index is, that's how many times we would have to go through that loop. So it's linearly proportional. After that, we have log linear. The nickname is not dash, it is log linear. We see this again frequently on algorithms that use trees. Eventually, we can get to the point where we see quadratic or cubic. This is where the variable is in the base of an exponent. The constant is the exponent. Why is that significantly better than if the constant is in the base of the exponent and the variable is in the exponent? Why does that make sense? Let's actually draw it out a bit, because I think this is a very fun exercise. I like to use base 2 to start, so we're gonna be comparing things like 10 squared, this is gonna be. It's gonna be. So what are these associated values? What is 10 squared? So we have 100 on this side, and what is 2 to the 10th? Does anyone know what that is on the top of their heads? Yeah. It's pretty close to 1,000. So I have this embedded in my head that any 2 raised to a power of 10 is pretty close to so 2 to the 10th is very close to 1,000, 2 to the 20th is very close to 1,000,000, 2 to the 30th, closer to 1,000,000,000. You can use that as an approximation. It's not perfect, and it starts to get a little bit less and less and less accurate the more you scale that, but it's a good just headspace, very quick memorization of it's kind of sort of close to that. What is the difference between these? What is the ratio of the difference? 10 times bigger? Great. Now we are going to change up this value. So this is the value of the base. We're holding this constant. So this was our n, and this was our constant. We're going to switch this up, and we can do something like, let's change n to be a little bit bigger. In fact, let's scale it by 10. What is 100 squared? 100 times 100? 10,000. We know this because we just have to duplicate the number of zeros here. This says double the number of zeros, so we just take the original number of zeros and duplicate it, giving you 10,000. How about 2 to the 100th? If we take my approximation for how to write this number, it's going to be gross. So we have 1, 0, 0, 0. That's going to represent about 2 to the 10th. 2 to the 20th, 30th, 40th, 50th, 60th, 70th, 80th, 90th, 100th. Ratio of the difference. We'll just stop with a lot. So the idea is that as these numbers even multiply by 10, the associated ratio of the difference, you can see just how much worse exponential scaling is than anything polynomial. So comparing something like just quadratic to exponential, it's only 2 places different in the table. No, exponential is disgusting. It scales so much higher, so much worse than anything polynomial. So this is okay. This is not. If you write an algorithm and you find that its complexity is exponential, throw it in the garbage, start again. It's not going to scale. Questions about the associated scaling and ratios of these 2 orders? It's gross. So each one of these functions describes the associated asymptotic behavior. So what happens as n scales? There are 2 rules that will help us, given an actual mathematical expression, to be able to define the order of that function. The first is that if you do anything to a constant value, if you multiply by a constant value, divide by a constant value, add a constant value, or subtract a constant value, there is no change in the function order. This allows us to do something like if we had some function that said that we had 10n squared plus 4n minus 6 all over 2. Oh man, this simplifies way too easily. But the idea is that here we have dividing by a constant, so we can ignore it. Here we have subtracting a constant, we can ignore it. Here we have multiplying by a constant, we can ignore it. Here we have multiplying by a constant, we can ignore it. So the associated function reduces down to this when we apply this first rule for figuring out what the associated order is. So any constants, get rid of them, they don't matter. Second, if you add or subtract a function in a smaller order, it does not change the function order. So here we see that we added something of smaller order. We took something in the quadratic order and we added something in the linear order. This tells us we can get rid of the plus n. So the entire function that I wrote below is in order n squared, it is quadratic. This does not define the entirety of the function, but it tells you how it is going to scale as n becomes very, very large. The constants, as n gets larger, have less and less and less importance. So while they do technically make a difference, the difference becomes close to 0, depending on how far out n scales. So we only care about that which actually changes the associated scaling as n becomes large. So let's try this again. 5n cubed plus 2n squared minus 4n plus 11. What is the order? N to the third. We can get rid of all constants. That's a constant, that's a constant, that's a constant, and that's a constant. Those are gone. So now we have n cubed plus n squared minus n. The second rule says adding or subtracting a function of a smaller order doesn't change the function order. Since n is being subtracted here from something that is a higher order, we can ignore it. Since n squared is being added to something of a higher order, we can ignore it. So we'll go back to our old example. We have two competing algorithms to accomplish a particular task. After we finish this, we found that they have the associated running times. One is an squared minus b log n, and one is cn plus d. First question I have for you, does it matter what the values of a, b, c, and d are? There's a reason they are variables. Doesn't matter what they are, we can ignore them. What if one of them happens to be 10 trillion? It's a large number. Does it matter? No. As n gets large enough, even that value will become minuscule compared to the associated scaling of the rest of these functions. What are the associated orders? Here we have something that is order n squared, and here we have something that is order n. Great. And we're out of time. So we will come back to this and get significantly more examples of this and make it just a little bit more complicated tomorrow. I have office hours right after this class. If you have any questions about the assignments, please don't hesitate to stop by and see me.